This is problem number 7 from chapter 4. The actual problem is down here, and we're going to answer this from A through F. 6 different colored dice are rolled. Of interest is the number of dice that show a 1. I found something online that would kind of simulate this, and this is random.org/dice. And what we're doing is we're rolling 6 dice. So we have 6 dice that we're going to roll. And the idea is to count how many ones pop up. So in this particular case, there's no ones. Let's roll it again. There's 1, 2. Here there's 2 ones. And so we would count that as 2 ones. Here there's only 1 1. 1 1. 0 ones. Let's roll it again. Nope. There's 1 1. Nope. There's 2 ones. 1 1. So we do this a bunch of times. We are noticing that there's either 0, 1, or 2. And I haven't rolled a set of 6 dice so far that would have more than 2 ones. It's not that it's impossible. It just doesn't seem very likely. So we should work out the problem, and that fact should reflect that idea. our distribution. Here's one with a 3 ones. Now trying to get 4 or 5 ones or even 6 ones would look like it's going to be really difficult. So that's what this problem is about, rolling 6 dice. Alright, so first thing it's asking is define in words the random variable x. So really what we have here is exactly what this is. So x in words is the number of dice that show a 1. And we should say it's out of 6 dice. So part B, list the values that x may take on. So if you remember, I'm going to draw the values of x down this way to get us set up for a table. Remember that our first roll we didn't get any ones, and we had these possibilities, or at least an experiment that we did. We had one roll where there was 3 ones showing, but there's 6 dice, so there really should be the rest of them. 4, 5, and 6. It's possible that you roll the dice and you get all ones. That's 6 ones that are showing, but we'll see that it's highly unlikely. So these are the possible values that x may take on. So give the distribution of x. So x, so what we're doing here is we're counting the number of ones. So in our roll there are 6 possibilities, or we have 6 dice. So let's see if we can answer this. Out of 6 dice, we either get a 1 or not a 1. And so, and each die is independent from each other, and we have a constant probability of 1/6 to get a 1. So probability that we roll a 1 for 1 die is 1/6. So this looks like it's a binomial distribution. You either get a 1 or not a 1. So that's the binomial part. That's the one of 2 choices part. And then we have a constant probability for each of those 6 experiments. So n is equal to 6. And p, little p, is equal to 1/6. So in our binomial distribution, we denote this distribution by a b, and then there's a parentheses, and then we put an n. That's the number of experiments we have, and then the probability of getting that is 1/6. So this is our distribution. So let's write that down here just to make sure. This is a binomial distribution. So n is equal to 6. That represents a sixth die. The probability is of getting a 1 is 1/6. So that's our p. Alright, let's move on. On the average, how many dice would you expect to show a 1? So we can probably answer that using some probability, but what I'm interested in doing is filling up the rest of this table. Or I guess before we do that table, we can talk about a particular term that we'll be using called the expected value. And the expected value in probability distribution language is the same thing as the mean, or mu. And there is a formula for finding the mean from a probability distribution function, but that formula, that particular formula, is a little bit more complicated. So what we do is we note that we have a special distribution here for binomial distribution. The mean, or the expected value, is n times p. So since we have the n and a p, we can compute that. That's n is 6, p is 1/6, so that's equal to 1. So the expected, when you roll 6 dice, the expected return is that one of them is going to show 1. Let's go back to our experiment. If we roll the die here, this is kind of like what's expected. Now there's going to be some rolls where you can have 2, and some rolls that you can have, well, this is 2 again, and then this roll didn't have any 1s. But in the long run, when you do this, say we took this experiment like 300, 400, or maybe even 1,000 times, and at each time we counted the number of times we get a 1, or how many 1s we get. If we take the average of all that, it's going to average to about 1. So that kind of makes sense. So that is our expected value. That's 1 is not referring to the 1 on the face of the die. 1 is referring to the number of 1s that would come out. Okay. Alright, let's see if we can answer part E. The probability that all 6 dice show a 1. So all 6 of them show a 1. Well, in one probability that all 6 dice show a 1, if we look at this distribution table, what we're really looking for is the probability from this binomial table over here, binomial distribution table, that all 6 die show a 1. So that's this last one over here, 6. So that's a probability. Actually, another way to state this is that your random variable is equal to 6. So again, there's a formula for this. There's 2 ways to do this. One is to do this using probability, and then the other is to use the idea that we have a binomial distribution. So in probability way of doing this, what we're going to do is we would essentially multiply 1/6 for the first die, and there's a 1/6 chance of getting a 1 for the second die, and a 1/6 chance of getting a 1 for the third, fourth, fifth, and sixth. So this is 1/6 to the 6th power. which seems to be, since it's in the denominator, it's going to seem to be a really small number. Well, let's figure it out since we have our calculator out. Let's type in, let's start up with a parentheses, 1 divided by 6, and then raise it to the 6th power. So this looks like this -5 over here as the power, and it tells you to move this decimal point 5 places to the left. So let's see, we'll write that as 0.1, 2, 3, 4, and then the 2, 1, 4. We can stop here. I'll just say this is a really small number. Okay, so that's one way to do it, and that way of doing it is a probability way. The other way to do it is, because you know that this is a binomial distribution, we're going to use our calculator. And if you go to Frank's workshops, you'll see that he'll teach you how to use this. But this involves a special command called binom PDF. And then for the binom PDF, it's going to require you to enter your n, which is equal to 6. It's going to require you to enter your p, which is 1/6, and then it's going to require you to enter your x. In this case, x is equal to 6. So let's see if we can do that in our calculator. So to get the binom PDF in your calculator, it's under distributions, which is above vars. So we'll hit the second function, hit vars, and then scroll down till you see binom PDF. And when you get there, you'll notice that there's a CDF as well. So for this particular problem, we're going to use a PDF. So let's hit enter, and we want to enter 6, a comma, and then a 1 divided by 6, and then another comma, and then our x value is 6. So let's see what this is going to be. You'll see that it's exactly the same thing that we got from before. Same answer, two different ways, one using probability and the other one using the binom PDF. Now the next thing they ask is that, is it more likely that 3 or 4 will show a 1? How many is it more likely to that 3 or that 4 dice will show a 1? Use numbers to justify your answers numerically. It looks like we got a 3 in our experiment at least one time out of however many times we did it, and we never got a 4 or a 5 or a 6. So it seems like as you get further out, your probabilities will get lower and lower. So it would seem like it would make sense, but it says to justify your answer numerically. So at this point, what I'd like to do is take advantage of this list that we have. We have a list from 0 to 6, and our probability distribution table takes our random variables and assigns a probability to them whose sum add up to 1. So when we add up all these numbers, we should get 1. But first, let's see if we can actually come up with those numbers. So each of these things represent a probability. In fact, this one over here, let's call this 2.14 e to the -5th power, or 2.14 times 10 to the -5th power. We know that value for the 6 already. So let's figure out the rest of the values. Now we can do this one by one with binom PDF 6, 1, 6, and then 0, binom PDF 6, 1, 6, and 1, binom PDF 6 and 1, 6, and 2, etc. But if you're interested in filling up a whole table, what you can do is you can go to your list and fill it up automatically. So let's take a look there. Let's go to Stat and Edit. And your L1 will contain your X values, your random variables. Now to populate your L2, let's move the cursor up. Notice my cursor is up here. Another thing to notice is this is L2 without any parentheses. So while you're up there, let's run this binom PDF function. So second function in distributions, look for the binom PDF again. So the PDF, and this time we're going to enter 6 comma 1 divided by 6, but we're not going to specify an x value. If you don't specify an x value, your calculator will populate a whole list, and that's exactly what we're doing. So let's close the parentheses and press enter, and here we go, we have the list. So it looks like there's about a 33% chance that you would get no ones, and a 40% chance that you get 1 1. Now there's a 20% chance that you're going to get 2 1s, and a 5% chance that you get 3 1s. So if we did this experiment with that simulation about 100 times, we should expect to get 3 1s about 5 times. And 4, now that's less than 1%. And then 5 and 6 would even get you smaller probabilities. So I'd like to write this down in our table. 0.3349, 0.40188, 0.20094, 0.05358, 0.00804, and this is 6.4 times 10 to the negative 4th power. And then that last one, we'll see it's the same again. So is it more likely that a 3 or a 4 will show 1? And we can justify that by saying, well, the probability that you get a 3 from this binomial distribution is 0.05358. A probability that in this binomial distribution that you're going to get a 4 is 0.00804. So clearly you have a better probability that it's more likely to get a 3. Because 0.05 is larger than 0.008. Alright, there is a lot to learn in this probability section, so let's work hard on this. This will give us a good foundation when we get into inferential statistics. Okay, hope that helps.